So we need to talk about the factor label method of making conversions or working problems, specifically when, well, you'll see, okay? So we're going to take it up a notch. We're going to square and cube things. So for instance, we know within the English system, 1 yard is exactly equal to 3 feet. Okay, but what if you had, and the next picture shows you, what if you had 1 yard by 1 yard? Okay, to get the area you take, that'd be like 1 yard squared, right? And so the question would be, how many feet squared do you have? How many square feet? And some of you can kind of think through that. And actually, as it turns out, 1 square yard is equal to 9 square feet. Okay, so 1 yard squared is equal to 9 square feet. When I say 9 square feet, this is what I mean. Each one of those is like a little tile. Like in the chem lab, we've got floor tiles. Okay, and they are 1 foot by 1 foot. So each of these boxes is 1 feet squared, 1 square foot. Okay, so, but you can't just eyeball it like this. You need to be able to apply the factor label method. So, of course, 1 yard squared, this makes sense, right? 1 yard squared, we can break those up to 3 feet and 3 feet, and then 3 times 3 is 9. The units of feet would be squared, right? 9 feet squared. Okay? So we could go ahead and work this. 1 yard squared is equal to how many feet squared, using the old, start with the term that you want to convert, in this case 1 yard squared over 1, okay? And then if we want yards to cancel, be left with feet, so we're going to put 3 feet over 1 yard, but we have to do that twice because we need yards squared to cancel. So this is the thing I want to convert, and this is the relationship between yards and the thing I want to get to, which is feet. So now, you know, what we've been talking about is that yards squared cancel, and we're left with units of feet squared, which 3 times 3 is 9, right? So we have 9 square feet. That's it. Alternatively, on the previous slide, when we had 1 yard squared over 1, and then we had 3 feet over 1 yard, 3 feet over 1 yard, we could collect those two terms, and that's equal to quantity, 3 feet over 1 yard, quantity squared. Just be careful, and this is just quite legitimate to do, but I think I have a slide here to remind you that this square goes in and you need to apply it to both the numbers and the units. The number and the unit. Okay? If you ever do it that way. So taking a whole quantity and squaring it's great, but just don't let it come back to haunt you. Well, we're not so interested in the whole area thing as we are in volume. So, of course, that adds one more dimension. So the volume of a cube would be length times width times height. Yeah. So taking it up a notch then, okay, if we were to go back to within the English system, converting 1 cubic yard to how many cubic feet, okay, it would look like this. 1 cubic yard, and my yardstick up here, which is a meter stick, which is almost a yard. Okay. So this in a cube form, okay. So what is 3 cubed? 27, exactly. So we could write a relationship 1 yard cubed is equal to 27 feet cubed. We totally could. Okay. So for sure. So let's go ahead and work a problem that involves volume. So anytime you see length raised to the 3rd power, you're talking volume. Length raised to the 3rd power is volume. So how many cubic feet cubed are there in 22.0 inches cubed? Okay. So that's within the English system. 1 foot is equal to 12 inches exactly, right? Okay, so the first term we were going to write down is going to be the thing we want to convert. Oh, here's my kind of flow chart. Remember, we kind of write this ahead of time, our approach to working the problem. So we're going to convert from cubic inches to cubic feet. So we can go from cubic inches directly to cubic feet based upon the whole 1 foot is exactly equal to 12 inches. But remember that we need it cubed, okay? So you guys told me 3 cubed was 27, right? Right off the top of my head, I don't know what 12 cubed is. But my calculator has it, okay? So there's different ways to show your work for this problem. I'm just going to kind of show you one, maybe some variations on this. The thing we want to convert is the first term over 1. 22.0 inches cubed over 1. Okay, so if I go ahead then and insert the ratio, the conversion factor, 1 foot over 12 inches quantity cubed, okay, that will do it for me with regard to units canceling that need to cancel, okay, and we'd be done. I think I have some breakouts under here, maybe not. So try this in your calculator if you want. We've got a minute. You get to find your y to the x key probably. Let's see, mine looks like divided by 12. Or can we just use the caret? I think so. I didn't have the y to x, but I had a caret key. So, which makes me think of carrot cake, which makes me hungry. I love the feel of the calculator. Sometimes just like, oh, you know, and then when you get the right answer, like, oh, I just really love it. Now, do you see why this is rounded to 3 significant figures? Because there are 3 in the 22.0, that trailing 0 after decimal significant, 3 significant figures there. No uncertainty brought by the 1 or the 12 in the middle term. And then giving it 3 sig figs, of course, this one is not significant. This 0 is not significant, but 127 is. Any questions about that? Okay. So just to kind of break out what this quantity means, it means 1 foot over 12 inches 3 times. Alternatively, or really what you're doing then, is cubing both the numerator and the denominator. What I've told students some semesters is I really would encourage you just to write it out 3 times. Because then you don't have to remember to take the cube into that number. That's the biggest mistake I see. So you could just insert those 3 terms in for that 1 term. All right. So let's do another one. Sometimes working a problem kind of helps to get your wits about you. So you see the L, of course, that's metric volume. And then you see the inches cubed, you're like, oh, that's English, right? Length cubed is volume, so that's English volume. So somewhere we're going to have to cross the imperial metric bridge, right? So a strategy coming up. Okay, this is a classic that we're going to go from English to metric using that one you're supposed to memorize. So really avoid looking up equalities on the internet, okay? Because I would expect you to be able to do this on a test. Yep, 1 inch is exactly equal to 2.54 centimeters. So we can get from cubic inches to cubic centimeters like that. Of course, once we get cubic centimeters, it's downhill to get to liters, right? But we probably need to go through milliliters. Relationship, what's the relationship between cubic centimeters and milliliters?
It's like 1 to 1.
It is 1 to 1, yep. 1 milliliter, 1 cubic centimeter is exactly equal to 1 milliliter. And then we can go from milliliters to liters. What's the relationship there?
1,000 milliliters equals 1 liter.
Yep, 1,000 milliliters is equal to 1 liter. Exactly. Any questions about that? So that's the strategy. So let's go ahead and execute that. So the first thing we want are the inches cubed to convert over 1. 25.0 inches cubed over 1. Then we're going to go from inches cubed to centimeters cubed. Since we want inches cubed to cancel, those units are going to go in the denominator. So it's going to go, what, 2.54 centimeters over 1 inch quantity cubed. Does that make sense? And then we want centimeters cubed to go away, to cancel. So we're going to put cubic centimeters in the denominator. So that next term is going to be 1 milliliter over 1 centimeter cubed. Whoops. And then what's canceled is inches cubed have canceled, centimeters cubed have canceled, and we have milliliters at that point. So we need to put units of milliliters in the denominator. So 1 liter over 1,000 milliliters. 1 liter over 1,000 milliliters. And that's it. So try this on your calculator, but also when we round it, looks to me like we have to count the uncertainty in the 25.0 inches cubed, but there's no uncertainty brought by anything else. So 3 sig figs. Is this what you got? So we do have to put the trailing 0 after the decimal. So 0.410. I heard one yeah. I saw another head nod. Any questions? Okay. Did we all get that? I couldn't tell. Are we punching buttons? Is that your calculator?
Yeah.
Oh, but you, oh, so you can do it without the, you just multiply it by itself sometimes. Cool, cool. But usually,
I don't, yeah, I don't know. So when I'm putting them all in.
oh, here it is.
Yeah. So
Okay.
then I just cube everything while I'm solving.
So I would put in 25.0 and then 2.5. Oh, let's see, how do you do that? I see what you're saying.
You want me to cube it before or cube it after?
Maybe I cube it before, so clear that up. So go ahead and put in 2.54 and hit that, and hit 3, enter. Okay, now go ahead and multiply 25, enter, and then divide by 1,000. Does that seem right?
Yeah.
Yeah, that's, every calculator is a little different. Did you have one like hers, did
Yeah.
you figure it out?
Yeah.
Yeah, well, yours is a little different. Okay, very good. There's yours, with the carrot key too. Okay, so let's take a look at these. These are due on Wednesday. We're at the end of it, okay, good. So I have a hints sheet. Sometimes I don't quite know about my hints sheets. They're kind of silly. But where'd you go? There you are. Yep, that must be it. Is this it? No, that's not it. Drat. What did I call it? That's the next one. Maybe I called it this. Does that look right? Yes. Okay, good. So there's 4 problems due Wednesday. These are the first 2. So the first one is about area. And if you're like me, I had to look up what H meant in the metric system. Oh my gosh. So hecto means 100 times the base unit. You know, 1 kilo means 1,000 times the base unit. Hecto means 100 times the base unit. I mention that because you're going to need to use that. So 1 hectare is equal to 1 hectometer, or 1 square hectometer, HM squared. Okay, so that's that. There's a 1-to-1 relationship. And then what I would do is go from hectometers squared to meters squared, realizing within the metric system, one hectometer is equal to 100 meters. And then I would go, if you read the hint at the bottom of page 37, it's kind of wanting you to go this route. So I would go from meters squared to centimeters squared. Now remember, when you do this, you need to square those, the number and the units. Okay? So I would go from meter squared to centimeter squared. Then I would go from centimeter squared to inches squared, kind of like we did a little bit ago, 2.54 centimeters exactly in 1 inch. Then I would go from inches squared to feet squared. I know it says a subscript, but it really should be a superscript. Then I would go from feet squared to miles squared, and then miles squared to acres, because actually those equalities are given in the problem. So I'm just saying. For the next one, 38, then it gets easier after that, a little easier. Define easy, right? We have a few problems now where you're given a quantity, in this case density, in certain units, and you're supposed to convert to other units. So in this case, you're given density in pounds per cubic inches, which is great. And you're supposed to get to grams per cubic centimeter. And actually, you're going to need 2 conversion factors. This right here, I didn't put in the numbers, but of course you know it's 1 inch and 2.54 centimeters, right? Okay. If I put this right here, my inches cubed will cancel, which is awesome. It'll leave me centimeters cubed in the bottom. And then if I introduce this another term here in the end, this actually will get my pounds to cancel and I'll have units of grams. So notice everything cancels except for grams per cubic centimeter, and that's exactly what you're after. Okay. Fair piece of a hint, but not too bad. The more you do these are here to stay. This whole idea of watching what the units are and making things fit so you get the right units. That's how you work chemistry problems. You don't really have to know anything. Well, kind of, right? Okay, so the other 2 look like this. Question 39, again, it has a pounds per square inch, okay, and you're supposed to convert that. There's actually 2 parts to it. It says, what is this pressure in grams per square centimeter, and also kilograms per square meter. So actually, question 39 has 2 parts. Okay, and I just kind of said similar to 38. So you put your units, you clearly unpack what you're trying to convert, and then make the units where they need to be. And I can't remember. The next one's kind of, it feels random to me. It always does. Every semester when I get to this, it feels random. But see what you think. Basically, they've taken a blood cell, and blood cells are not spherical per se, but they're going to go with a sphere. That's what it most resembles. And they say the volume of a blood cell, and they give it in cubic centimeters. Okay, what is the diameter of a red blood cell in millimeters? So and I wouldn't give this to you on a test, but inside the back cover of Petrucci's textbook actually has the formula for a volume. So volume is 3/4 pi r cubed. So actually, we can get R cubed from this in centimeters, right? Okay, then we have to convert that to millimeters. Don't forget, that is actually going to be your R, so of course diameter is twice that. Okay? Any questions? All right. So on to finish up the other part. I don't know where it will necessarily fit in throughout the semester, but you guys have a, how do I say this? There is another class kind of tootling along through the same information that you guys are tootling along through in West Burlington. And it's taught by my husband. So there are two Snipes in the catalog. Yeah, he teaches the West Burlington chemistry. So I mentioned this because what they did was they went straight through part 4 and then the beginning of part 5. And I broke it up, part 4 and kind of stopped at cubed, then went on to, that's okay, either way. Okay, so a theme of the semester is to basically take numbers like density and velocity and percent and to unpack those numbers before you can use them in a chemistry problem. So we're going to do some types of conversions based upon this solution that is 7.2% sucrose by mass. And we actually already talked about that, what that means. So we're going to unpack it here in a minute. But whenever you look at a property, the units of the property kind of tell you how you can use it. So for instance, when we unpack 7.2% by mass, it's going to be 7.2 grams of sucrose per 100 grams of solution. Grams of sucrose, grams of solution. Those are the two things we can use this to go back and forth between. So we're going to do that. The first one is how many grams of sucrose, so that's going to go on the right. Okay, are there in 75 grams of solution? That's going to go on the left. That's problem number 1. So that's what a mass of solution to grams of sucrose. The other one is what is the mass of solution that would contain 3.3 grams of sucrose. So we're going to start with sucrose and end up with mass of solution. So here we go. Here's that 7.2% unpacked. And just kind of like we unpacked density before, you can kind of say unpack it in 3 different ways. There's the straight up 7.2 grams of sucrose per 100 grams of solution. Now this is, I've seen us stumble, students and people using this. Do you see where we have 2 masses? You have to be what we call explicit. You can't just say grams over grams. You have to put grams of sucrose over grams of solution. The inverse about this solution is also a great property. In 100 grams of solution, there'll be 7.2 grams of sucrose. We could flatten it out into an equality for this particular solution. 7.2 grams of sucrose is equal to 100 grams of solution. So just unpacking it. Just say no. Just kidding. So here we go. Let's go ahead and work those 2 problems. So if you go ahead and clearly write the term we want to convert and put it over 1, so 65 grams of solution over 1, then you see that we want grams of solution to cancel, so we're going to go with the unflipped version of weight percent. 7.2 grams of sucrose over 100 grams of solution. And bada boom, you're done. You know you're done because your units have canceled and you're left with the units that you want to be left with. So, fingers, how many sig figs do we need to round this to? Peace. Yep, very good. 4.7 grams of sucrose. This could be a very practical exercise if you're trying to, it could just be very practical. So the next one is we were given the mass of sucrose and asked to find the mass of the solution. So now the starting term is 3.3 grams of sucrose over 1. We want grams of sucrose to cancel, so we're going to use the inverse, aren't we? The flipped version. So now this next term is 100 grams of solution over 7.2 grams of sucrose. So grams of sucrose cancel, we're left with grams of solution. Again, two significant figures, right? Pretty straightforward. 64 grams of solution. Your calculator matches your shirt, Sarah. It's like she's color coordinated. Okay. Well, we kind of finish up then. This is, you have several homework that are going to be due, and this is kind of the sort of problem it is. We have one solution, okay, and we know both the weight percent and the density of the solution. We're going to unpack those two numbers and use them kind of as puzzle pieces to get where we need to get to. So HNO3 is nitric acid. One of the things, if you're like me, you have to kind of concentrate on, okay? I don't know if this makes sense to you. So you grab a bottle of HNO3 in the lab, right? The stuff is, in its concentrated form, is kind of nasty. Okay, it can make your fingers turn yellow if you get it on you and don't get it off you fast. But when I grab the bottle or pour it into a beaker or something, HNO3, pure HNO3, it's not pure HNO3. It's like, I can't remember, like 36% by weight. Okay, so in that I have some, my purple dots there, I have some HNO3, but the rest is water. Okay, I just mentioned that because I don't know if that. So here it says that we have 22.0% by weight HNO3 and the density of the overall solution. Maybe this is where I'm going with it. So here we go. The weight percent is kind of straightforward. Anytime you're given the density, that is of the entire solution. It's the entire solution. They didn't like pick out the HNO3, get a weight, get a density, and pick out the water, get a density. They took out the HNO3 plus water to get a density. So that's the density of the solution. So let's go ahead and work this. So we're going to unpack those. And now, in this case, what you're going to see here in a minute is 75.0 grams of pure HNO3. When you remove all the numbers, like the constants, like weight percent and density, whatever number you didn't use, that's what you're going to start with, okay? Really, it kind of works that way. And we're going to have a few steps, but ultimately, we're supposed to, what is the volume of solution you must use? So question mark, liters solution. That's kind of how it's going to go. So here's unpacking. So 22.0, don't forget the trailing zero after the decimal. So there's 3 sig figs in the weight percent. 22.0 percent HNO3 means 22.0 grams of HNO3 per 100 grams of solution. The density, like I said, is the whole solution, whole enchilada. So it's 1.13 grams of solution per 1 milliliter of solution. So if we're careful with labeling, this should go just fine. So we know, like we saw before, you can use the inverse of those as needed. So the first term is going to be, like I said, the only number you didn't unpack. Okay, so we can go from grams of HNO3 to grams of solution using the weight percent, the mass percent. And then we can go from grams of solution to actually just milliliters of solution using the density. That's it. So the first term is that 75.0 grams of HNO3. And if you look by definition, then we want, at the previous slide, we want grams of HNO3 to cancel, so we're going to have to use the flipped version of weight percent, aren't we? So it'll be 100 grams of solution over 22.0 grams of HNO3. So now our grams of HNO3 have canceled. And we have grams of solution. So we're going to use density to get to milliliters of solution. So it looks like we're going to have to flip that one too, aren't we? 1 milliliter solution over 1.13 grams of solution. So that's the density. And we're done. So looking like 3 significant figures. Actually, there's uncertainty brought by each of those terms. But we've got 3 significant figures in all of them. So you should get, in your calculator, 302 milliliters of solution. If I'm ever like working problems up here and I go too fast, let me know. Let's slow it down. Okay, so let's take a look at the other problems that are due for Wednesday. So you guys handed in 55 and 56 today. And the other ones, I know because I found those before. They look like this, don't they? Good. And they're very similar to that last HNO3 problem we did. So 51, they give the weight percent and of acetone in a solution, then they give the density of the solution. So I went ahead and in blue and purple there, I unpacked those for you. So after that information's given, also notice that they give 91.5% water by mass. You don't use that number, but it's the difference from 100 of 8.50. What mass of acetone in kilograms is present in 7.5 liters of solution? So 7.50 liters is what you're going to start with. Notice you're going to have to kick it over from liters to milliliters using the 1,000 relationship. And then once we have milliliters of solution, we can get grams of solution using the density. And then once we have grams of solution, we can get grams of acetone using the weight percent. Don't forget, it's wanting it in mass in kilograms. From grams. The next one. Again, you see weight percent. I was doing this in my office. I'm like, well, where's the density? And I read it a few times. I'm like, you don't have to use density. It's kind of a strange one. So anyway, it says, gives you the weight percent of a sugar solution, and it says what mass of solution is needed to obtain 1.00 kilograms of sucrose. So it's like an easier one, right? It's like, really? Okay, so that's 52. Remember that like 51 and 53, the answers are under doc sharing. So 53 is relatively straightforward too. Okay, they give you the percent by mass of nitrogen in a fertilizer. And they want to know what mass of fertilizer do you need to set aside in kilograms if you want 225 grams of nitrogen. You can't go wrong with unpacking the weight percent and the density. Very rarely will I give you a problem where you don't have to use the numbers. I think that's cruel. So you usually have to use all the numbers. Sometimes temperatures, I just give temperatures because they're important, but you don't use the temperatures. So that one's not too bad. And then the last one, This one's back to like we did with nitric acid. We have density and weight percent of acetic acid and vinegar. This is one of those where I'm like, well, yeah, vinegar is acetic acid, but it's not a pure acetic acid. Okay, so vinegar is the solution. Vinegar is the solution. Water plus acetic acid equals vinegar. Okay, so the density of vinegar or the solution is given. The weight percent of acetic acid in vinegar is given. And then you're supposed to go from 1 liter of solution or vinegar up to grams of acetic acid. So, okay, they're all great. Any questions? So that's all I have today. We'll see you on Wednesday. Remember, Wednesday we have a study session.